So in this video we will look at two examples of KVL and KCL and branches and loops and the theory covered in the previous video. The basic theory is outlined here. So for KVL, the sum of all the voltages in a loop is equal to 0. With KCL, the sum of all the currents in a node is equal to 0. And Ohm's law is V equals IR, where V is the voltage, I is the current, and R is the resistance. Okay, so let's start this example. This is an example circuit which is given to us. It has some sources, it has some resistances, and we are asked some questions about it. So the first question is, what is the number of nodes and branches in the circuit? So the number, let's first look at the number of nodes. So how do we count the number of nodes? Well, the number of nodes, a node is any connection, a single connection between a number of elements within the circuit. So this over here would be our first node. That's 1. This over here would be our second node. So that's 2. This over here, be careful of that, would be our third node. Don't miss that. Fourth node and fifth node. Sixth node, seventh node. So this circuit has 7 nodes. They also asked for the number of branches. Okay, so branches. So what are branches? Branches are the elements within the circuit. You just add them all up, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 branches. 10. So that's the first question done. Second question says calculate VI. So what is VI? Let's look for VI. So VI is this voltage of the source over there. So we want to know what is the voltage of that source. So how can we calculate the voltage of the source? Well, we can say, okay, let's apply KCL, which is the sum of all the currents, but this isn't really going to give us this voltage because we already have the current through here, which is 2 amperes. So if we add all the currents, we're just going to add 2 amps. We're not going to include the variable VI within that calculation. So it's not going to solve the problem. The other way is KVL, to sum all the voltages within the loop. So what we do is we draw a loop like that. And we say, okay, well, the sum of all the voltages within the loop, all voltages, loop equals 0. So we know all the sum of all the voltages within this loop have to equal to 0. So we know this voltage here is plus 10 volts there, so then it must be plus minus polarity like that, and the same thing here. So there are two ways to look at this problem. I'm going to do the KVL way first, which is the sum of all the voltages equals 0 in this loop. So if we approach it like this, then we're going to say it's minus 10 volts, or minus V1, plus VI, then we have to add this resistor as well. So we're saying that the voltage over that resistor, V equals IR, big R, and that would be 2 amperes through there as given, times the resistance of 3, which would give us 6 volts. So that would be plus 6 equals 0. We also know what the value of V1 is, so we can say that that is 10 plus VI plus 6 equals 0. So now I can simply solve for VI. VI is equal to take the 10 over, or the minus 10, which would become 10 minus 6, which gives us 4 volts for VI. Okay, so there's another way of looking at this. I call it the logical way. We say that this voltage here is 10 volts. Well, we know that this reference here is 0 volts because it's ground. Every circuit has to be grounded, by the way. So any circuit has to be grounded at the bottom. If this element here is drawn, then it's grounded. Usually, almost 100% of the time within first year circuits. So this is 10 volts here, and this, therefore the voltage over here from here to there must be 10 volts. So you can say that 10 or V1 is equal to Vi, which is this voltage, plus this voltage, because this is the only voltage from the top there to ground. So Vi plus whatever the voltage there is, which is 2 times 3, 6 volts like we said. So 10 equals Vi plus 6, therefore 4 volts equals Vi. The same answer. Okay, next question is calculate V3. So V3 equals, sorry, I messed up my 3 over there. I apologize. Okay, so how can we calculate V3? V3 is the voltage over this resistor here. Well, we can apply KCL, but again, we have IF, the current through there. So if we were to do KCL, we would add IF, which would exclude the variable V3. So it doesn't make sense to do that. So the next option is to apply KVL. So we want to use a loop that includes this element, and we already have some stuff worked out here. So the logical thing to do is to use that loop. So we're going to apply KVL in that loop. So KVL once again says the sum of all the voltages within the loop is equal to 0. So we started this loop. Once again, the polarity of this is that. So we already know that this 10 volts from there to there. So we can simply ignore all of this because we know the voltage from there to there is 10. And say minus 10, minus because we're coming from this side, minus V3 because we want to calculate V3, minus the source here. The voltage across this source is 1.5 I1, and we're approaching it from the negative side, minus times 1.5 I1. I1 we know is 2 amperes is 3 here, so we're just going to multiply it because it's dependent. It's a voltage, a current controlled voltage source. Note that here, current controlled voltage source, because it's a voltage source controlled by the current I1. So we're here plus V2 because we're approaching it from the positive side, not from the negative, but from the positive side, plus V2, which is 5 volts, equals 0. So now we can sub in for I1. I1 we said is 2 amperes. And if we simplify this, then we get minus 10 minus 3 plus 5 minus 10 minus 3 plus 5. If I take the V3 over, it becomes positive. And therefore V3 equals minus 8 volts. Okay, fourth question. Want to calculate IF. IF is the current over here. So if we use currents, then we say that the sum of all the currents in a node is equal to 0. So it would make sense to use KCL because we have IF here. We have 5 amperes coming in here, and we know the current through there is 2 amps. So it would make sense to do KCL at this node here. So KCL. KCL states that the sum of all currents into and out of a node equal 0. If it doesn't work, then we can simply try KVL, but in this case we can see that we have all the currents in and out of this node available to us, so it makes sense to use KCL. So I'm going to say that all the currents in are negative and all the currents out are positive. It doesn't matter. You can either say that all the currents out are positive and in are negative, or the other way around, as long as it's equal to 0 in the end. Okay, so that would mean that into this node we have 5 amperes, so that would be minus 5 amperes. 2 amperes is going out of this node, so therefore plus 2. And then IF is also leaving this node, so we say plus IF equals 0. And then it's simple to solve for IF. We just say 5, take the 5 over, minus the 2, take it over, and IF therefore equals 3 amperes.